Hello, my name is David Sandler. This is for the spring class of cs6263 Cyber Physical Systems. The paper that I will be discussing today is the Million Key Question, investigating the origin of RSA public keys. Quick acknowledgement of the paper. The authors are Peter Svenda, Mattis Nemec, Peter Seekin, Rudolf Kavanowski, David Formanek, and Vasek Matyas from Masaryk University in the Czech Republic. The paper was included in the proceedings of the 25th Usenex Security Symposium, which is August 10th through 12th of 2018. Quick introduction to what we'll be talking about today. We're going to first talk a little bit about the RSA system of public-private key exchange. We're going to go into an overview of public key attack methods and an intro into key leakage. Then we'll be going over the majority of what this paper is about, which is RSA key pair testing of commonly used software and cryptographic smart cards, which provide the keys which are used in most of these exchanges. Based off of these results, the paper talks about methods of fingerprinting smart cards in libraries based only off of the information provided by the public key. This information is then tested on real-world data sets, and the implication of these findings and the recommendations to mitigate this are what we'll conclude with. So a quick introduction to the RSA crypto system. Public key exchange is done through the generation of large prime numbers, P and Q, usually is what they're referred to as. Numbers computed, which is the product of these two large primes, and then phi n is the product of P minus 1 and Q minus 1. Exponent is chosen such that phi of n is co-prime to E, meaning they have no common factors. And then a private exponent D is calculated as the inverse modulus of phi n. Public key is En, and then Dn or PQ can be used as the private key, knowing that P and Q obviously can provide you N. The private key is only known by the user, and the public key is distributed out into the world, which allows people to privately sign things by only knowing that secret and allowing other people to authenticate that information on the other side. Therefore, when we attack the RSA crypto system, the way to do this is factorization of P and Q. You need to compute what P and Q are in order to do the math and come out with the private key. However, if P and Q are very large numbers, the math behind this becomes very expensive and can even reach the point where it's impossible to find an answer in any reasonable length of time. There are a variety of older methods of doing these attacks for factorization. However, if P and Q are too close to the square root of n, Fermat factorization can be used to more easily find P and Q by reducing the space that is required to search for them. Basically, if there is insufficient entropy in P and Q choice, they are more easy to factorize, and therefore the security of the exchange becomes at risk. Key leakage is basically information that's given by the public key, which allows the attacker to understand how that key was generated, what algorithm was behind it. Therefore, in order to make sure that the best practices are being upheld by public key exchange algorithms, it is sufficient to test them. And to do this, the authors of this paper generated 1 million key pairs from 22 different software libraries and 6 keycard vendors. They looked at differences in implementation when possible from open source, and then used the keys themselves to identify any sort of patterns when there were black box systems where they were unable to evaluate the code which generated the keys. So P and Q prime generation. There are a few established ways to do this. Fermat, Miller-Rabin, Solovey, Strawson, and Lucas tests are tests that are used to test a very large number to see, is it prime? Some libraries don't properly implement these tests and only allow very specific primes, such as Bloom primes, through, which makes it easier to identify as a prime generation method compared to other methods, as only specific prime numbers will be generated. However, the main two methods by which prime numbers are generated for P and Q are random sampling and incremental search. When we look at random sampling, numbers are randomly generated until one is found to be prime. And this won't cause a bias in the distribution of prime numbers selected for P and Q. The other method is known as incremental search, where you randomly generate an integer, and if it's not prime, you continue to increment that integer until a prime is found. However, primes are not equally distributed throughout the numeric space, meaning that certain areas have more primes in them than others. And due to this, you'll see that certain primes have what are known as large gaps, meaning that there's not the nearest prime before it can be 2 or 3 times the distance between two other primes in a similar numeric space. Because of this, these primes become more statistically prevalent. Additionally, OpenSSL, which is a very large, very widely used library with close to 90% of the market share, certain candidate primes are rejected with p-1 divisible by a large prime less than a very specific integer, which makes sense only if you're looking for what's known as a safe prime. I could go into what a safe prime is, but specifically, just to kind of give you the 10,000 foot view here, it's where primes are required to have a certain amount of space between them and the primes before and after them, which is useful for thwarting older attack methods. However, newer ones, this is no longer needed, and it makes it so that the library is more easily identifiable compared to other prime generation methods. Key generation. So the key size is the bit length of the modulus. Primes are going to be 1/2 the size of the modulus, or 1 bit shorter than that, depending on the size of the modulus and the rules that are enforced for that. K-bit primes are generated until the product is the correct length. However, the rejection criteria can make small moduli more probable if the smaller of P and Q is rejected. Rather than selecting a new P and Q each time, the product ends up being the incorrect number of bits. In order to solve this issue, square regions are used to bound the solution space of P and Q to make sure that they come out to be a specific length that they are meant to be. To further this point, you can even go even further and bound the bits, either the most significant bits or the least significant bits of P or Q, in order to make this solution even easier and make the key generation faster. However, the study also looked at black box implementations of RSA key and prime generation. Since they couldn't examine the source code, what they did is they generated 1 million RSA key pairs of 3 different bit lengths on a variety of widely used vendors, NXP, Gemalto, Infineon, so on and so forth. And what they did was, using the same sort of statistic analysis methods as before on the open source ones, and even looking at a few patents in the case I believe of G&D, what they did is they looked for variations in the most significant bits of each prime. And by doing this, they were able to identify ways that these primes were generated based off solely patterns in these primes and the keys that they provided. Because the moduli is the product of P and Q, there was no effort for uniform distribution across them. When we look at the results of this study, the most important one is that format factorization wasn't practical, as P and Qs were not close enough together in any of the software libraries or RSA key cards. Card-generated keys used a public exponent that was pretty constantly equal to 65,537, and most of the software libraries used the same public exponent number or user selectable number. The modulus value were almost always of the same required length, except in one case when I believe it was 2 bits less. P was not assured to be a safe prime number in all these cases, where a safe prime is indicated to be 2Q plus 1. Most of the cards required the P value to be greater than Q, with a few having a few modes that required the inverse situation. And this was again due to that MSB value being tied to a specific value, such as in the squaring method. Certain vendors used 1111 and other ones used 1001. Certain other cards produced very specific integers where there is a relationship between P and Q and N, where P and Q are congruent to the 3 mod 4 scheme, meaning that there is some combination of 3 mod 4 where you can put P and Q in and come out with a solution. Based off of this, certain probabilities allowed for the identification of RSA source methods based only from the public key information. An algorithm was trained on the data that was used and collected by the researchers, and this allowed for a probabilistic identifier, which allowed for the algorithm to predict based off of a certain set of keys, sometimes only 1 key, but in certain cases 10 keys or even 100 keys, to try and determine what was the source algorithm for these keys. These keys were put in groupings as certain key cards all used the same methods, and certain libraries also used the same methods for key generation. And based off this, the single key could be most probably identified 40%, meaning that it felt 40% confident that the top identified method would be how that key was generated. However, when batches of 100 keys were used, the algorithm was 93% confident in its top answer. But what's incredible, with only just 10 keys, the most probable grouping was selected 85% of the time, showing how few keys it was necessary in order to fingerprint what algorithm was used to produce it based only off of the distribution of public keys, using those prime P and Q numbers. What does this mean? Well, for the researchers to make sure that their algorithm was working properly, they used it on real-world data. In this case, what they did is they looked at TLS key exchanges, millions of them. And what they found was the statistics for the sources lined up very closely with what they would expect to see. That was OpenSSL would be the vast majority of the traffic as you look at major carriers such as Google, other major vendors, their market share of being about 86%, and then their probabilistic identifier was able to see that it was about 90% of the traffic used OpenSSL methods. They also showed that servers were much more easy to identify than other computers, and that they did a lot more key exchanges compared to your regular computer. Due to this, sources with fewer keys proved harder to identify than ones with many keys, as one would come to expect. What is the impact of this? Key generation methods are predictable, using only the public key. And when the number of exchanges is large, say 10 or 100 keys, they become highly predictable. To avoid detection, what we can do is we can look at our keys before we send them out. It's very easy when you generate a key to discard it and then keep randomly scrolling through keys until you pick one that fits a certain statistical model. And in this case, we know what the statistical model of 1 million keys from these algorithms looks like. What you can do is cherry pick ones in order to make sure you are selecting a certain level of entropy with your MSB. And to do this, you can kind of fuzzy the algorithm behind it. Additionally, certain key cards showed statistically identifiable key generation patterns, which again makes them more vulnerable to coordinated attackers who could hone their methods in to look for these specific patterns. What does it all mean? So the large conclusion was that all of the methods they tested showed a high enough level of entropy where format factorization attacks were not practical. However, by just looking at a handful of keys, source-specific information for the modulus allowed for the fingerprinting of how these primes were made, which would allow an attacker to, one, identify perhaps who generated those keys, and then secondarily, reduces the solution space that they would need to search by being able to look for primes that are far more likely to be selected than others. What this means is that far more information is given in the public key than what was previously assumed. And that in order to make sure that our public key exchanges for RSA are as safe as possible, we need to really make sure that we're using the largest amount of entropy in our P and Q prime selection. Otherwise, a sophisticated attacker can look at it and understand which algorithm it came from, and then use this to hone their attack. Thank you.